talk, Christiane. Maybe you can share your screen now. The title of the talk is What Chiral Molecules Can Teach Us About Quantum Control. So the stage is yours, Christiane, and I will give a 5 minutes warning before you have to finish. Okay?
Okay. Let me share the whole desktop, I think. Does that work?
Yeah. There are some black things.
Yeah, that's the Zoom
okay.
window, but now it should be minimal.
Yeah.
Okay,
yeah.
And you can hear me okay?
Yeah, perfect.
Perfect. Well, thank you very much for the kind introduction, a very extensive introduction. So out of the many things that I'm working on that you mentioned, I chose today to speak about chiral molecules because there have been some really interesting messages that chiral molecules have been teaching me and my colleagues about quantum control. So let me first introduce you to what actually means chiral molecules, and let's start with chirality. So chirality comes from the Greek word of handedness. So chiral comes from hand, and what do we mean by that? Well, it's something that you all know from everyday life. Namely, if you have the glove of a left hand, you cannot put it on a right hand. And similar with your shoes, you cannot put the shoe usually of your left foot on a right foot. So that's the phenomenon of objects being chiral or objects having a specific handedness. And that's something that you, if you look around, find a lot in daily life, in nature. For example, the way the snail's spiral is also handed. And the first person who tried to give this a more rigorous definition was the German philosopher Immanuel Kant. So what he said, and let me translate from the old German that's printed here on the slide, is what could be more similar or in every regard the same to my hand or my ear than its mirror image? And yet, such a hand, when seen in the mirror, cannot be put at the place of the original object. Because if this was a right hand, so in the mirror, it will be a left one. So he already understood very clearly that there is an issue with mirror images compared to rotations and translations. That's if we put this into more mathematical terms. Now, the first person who looked at chirality from a natural science perspective and saw that molecules also can have a handedness of their nuclear structure was Louis Pasteur in about 1850. He found that optical rotation, which had been seen before, so that the polarization of light can get rotated when passed through a crystal, that this is connected to the handedness of the molecules making up that crystal. And he did these experiments on tartaric acid, which is the molecule which is shown here on the slide. And for those of you who speak German, the German name is actually more pretty than tartaric acid, I think, because it's Weinsäure. And this phenomenon of chirality is something that continues to puzzle us until today, even though 1850 is quite some time ago. So one of the big open questions across, I would say, biology, chemistry, and physics is what is called the homochirality of life. Now, homochirality of life refers to the fact that essentially all amino acids and all sugars occur only in one-handedness, even though they could exist in both. But in biological materials, they are only found left-handed amino acids and right-handed sugars. And we really do not yet have a good explanation for this observation. And now maybe you think, well, that's an academic curiosity. Well, chirality of molecules is actually really important. And one fact where this becomes most obvious is in pharmacology. For example, in the late 1960s and early 70s, there was a big scandal in Western Germany where a drug that was supposed to calm people down caused birth defects when taken by pregnant women. And the reason for this was that one of the two kinds of handedness, these are called enantiomers. So one enantiomer of the molecule that made up the drug was actually toxic, and only the other one was the desired medication. And to make things even worse, within the body of a human, these two enantiomers could interconvert into each other. So real disaster. And that's not just an exception. Essentially, any molecule that is used as an active substance in drugs is chiral, and typically only one enantiomer is the drug, and the other one, in the best case, doesn't do anything, and in the worst case, can be toxic. So here's ibuprofen as something that maybe you know, popular painkiller, and it's the S-ibuprofen that you want. And by now, we've gotten smarter, and it's usually only the S-ibuprofen which is sold to you if you buy this in the pharmacy. So nowadays, pharmaceuticals are typically enantio pure. So bottom line is that knowing which handedness you have in a molecule, or in other words, sensing chirality, is something really important. And sometimes we get lucky. So here's the example of the molecule of carbon with the structure shown on the top. And incidentally, the left-handed enantiomer smells like caraway, whereas the right-handed one smells like peppermint. So in the case of this specific molecule, our nose already does the job of sensing chirality. Now, as scientists, of course, we don't want to rely on our nose. We can have a cold and then it doesn't work. What we usually, in physics in particular, would like to do is use external electromagnetic fields to tell us which chirality we have, which handedness of a molecule. And in that respect, the last 10 years have been extremely exciting because 3 new types of experiments have been developed and have really revolutionized the field. One was that you can determine absolute configuration, and that is something that was actually done in Frankfurt, so right next door to the organizers of this nice conference. And what was done in this experiment in the group of Reinhard Dörner was that they Coulomb exploded chiral molecules. So they just broke the molecules apart with an electric field and then did a coincidence measurement. And because they were collecting all the fragments in coincidence, they could reconstruct the original geometry of the molecule and see exactly which fragments corresponded to left-handed molecules and which to right-handed ones. Now, this is the experiment. I will not speak about any further in my talk, but rather I will focus on the two other types, which is 3-wave mixing using microwave radiation and so-called photoelectron circular dichroism. And I'll explain what each of these 2 techniques refers to in more detail. For the moment, what is important is that for these 2 types of experiments, what we have are chiral signatures that are observable, even though for the description of the interaction of the molecules with light, we only need the electric dipole approximation. And these experiments are done on randomly oriented molecules. So we will have to average over all orientations of the molecule in the gas phase. And that's important if you think that, left-handed molecules can look this way or that way or this, and similarly right-handed ones. And yet you get a chiral signature only using electric dipole interactions. Okay, so let me start with the photoelectron circular dichroism. What is this? So circular dichroism usually means that you're sending in light, which is circularly polarized, and you do this with left circularly polarized light and right circularly polarized light. You measure, and whatever you measure, you take the difference between the left and the right. And if you have a chiral object, this difference is not 0, and that's what's referred to as circular dichroism. Now, photoelectron circular dichroism means that you ionize the chiral molecules, in this case using 3 photons, and you measure the outgoing photoelectrons in a momentum resolved fashion. And then you get images like the ones shown here. And I should point out that this experiment had been done by my colleagues at the university in Kassel in the group of Thomas Baumert. And so this is the photoelectron image that you get with left circularly polarized light, that with right circularly polarized light. And if the molecule that you had been ionizing, in their case camphor, shown here, is chiral, then you take the difference, and even though this looks fairly similar, the difference is not zero. And this difference reflects a forward-backward asymmetry in the photoelectron angular distributions with respect to the light propagation axis. So that is the phenomenon of photoelectron circular dichroism. Now, if we look at the theory of circular dichroism, the surprising point is that, again, this is a purely electric dipole effect in case of photoelectrons. Why is this surprising? Well, let's look at the phenomenon that Pasteur had investigated back in 1848 about. Okay, so the traditional circular dichroism means that the polarization axis of the light is rotated, and the rotary strength of the transition on which you are exciting is given essentially by the scalar product between the electric dipole moment of that transition and the magnetic dipole moment. And since the magnetic dipole moment is usually very weak, this effect is usually very weak. But bottom line is you need this magnetic component of the transition, otherwise you wouldn't see anything. Now I'm telling you, here we see something and we don't need this magnetic dipole. And that's also the reason why the effect is actually quite large, because we only need the strong electric dipole. And the big difference between the traditional circular dichroism and the photoelectron circular dichroism is that one is a scalar observable, whereas the photoelectron circular dichroism is a vector observable. So what do I mean by that? Well, we can write, in theory, the photoelectron angular distribution, what is measured and shown in these pictures here, as a cross-section. And this cross-section we expand in Legendre polynomials. And then we can use, just to understand the essence of the effect, perturbation theory to see what determines this cross-section. And perturbation theory to lowest order, first order, means we have an electric dipole transition from some initial state to some final state with photoelectron momentum in the continuum. And this epsilon here is the polarization direction of the field. Since the experiment is done in the gas phase, so the molecules are randomly oriented, we have to integrate over all orientations. And now, when do we get the dichroic signal? Well, if you look at this expansion in Legendre polynomials, and we take the difference between left and right, then it is the odd terms which are relevant here. So our question is, when does the first order contribution from this cross-section does not vanish? And a very easy way, or maybe not easy, but a very elegant way to understand this has been brought forward by my colleague Olga Smirnova, the Max Born Institute in Berlin, and her student Andres Ordóñez. They introduced so-called molecular vectors, that is just the matrix element of the molecular dipole moment, and the field vector that characterizes my excitation laser. And then you can show that the first order contribution, the lowest order odd contribution, is given by an integral over a vector triple product of molecular vectors, namely for the two transition dipole moments and the k vector of the outgoing electron. And it is this k vector of the electron that makes this a vector observable, right? Because you measure angularly resolved. And it turns out that having such triple products is what is characteristic for chiral vector observables, for observables that allow you to sense the chirality of your molecules. Okay, so here's once more a sketch of the experiment, like my colleagues in Kassel envisioned it. So they have a molecular beam, and then they send in a laser and they circularly polarize this laser ionizes, and they measure the outgoing photoelectrons, and what is shown here are the momentum wave function of the photoelectron that then leads to these pretty images. Okay, so that's the phenomenon of PECD, photoelectron circular dichroism. Now, the question that we have been asking ourselves in my group is, can we control it? Can we make this observable larger or smaller just by changing the electric field that ionizes the molecules? And why does this question make sense? So let me step back a little bit and start with something that you've all seen before and refer to what is the essence of quantum mechanics. The essence of quantum mechanics, one way to see it, is that we have the superposition principle, which reflects wave-particle duality. And Bohr, back in the 1920s, phrased this in terms of this Gedanken experiment, where he sends an electron through a double slit and then sees this interference picture. Now, what is beautiful about this idea is that nowadays, it's not a Gedanken experiment any longer. It's actually a real experiment. For example, in Vienna, in the group of Markus Ahn. So here's a sketch shown from that group. And what they measure are really interference patterns, just as Bohr had envisioned them, using molecules that are sent through a grating, not a slit. That's essentially the only difference. So what does this have to do with control? What we know from quantum mechanics is a molecule can interfere with itself. And the point here is a single molecule interferes with itself. And now in quantum control, we use the same idea, just that the interference now doesn't happen in real space with a grating, but happens in Hilbert space, where we can build excitation pathways. So for example, instead of a double slit, if we have two different excitation pathways, one where we excite a molecule with a single photon, the one in blue here, or one with 3 photons, then this is identical formally to the double slit idea, and it is the relative phase between these two excitation pathways that controls how much population will end up in this final state. That's the idea of coherent control. So by controlling parameters of the external field, like their relative phase, we can build interferences essentially at will. Okay, now let's try and check if we can use this idea for controlling photoelectron circular dichroism. So here's the corresponding Hilbert space picture. We have the ground state of our molecule, and we can excite, for example, with a single photon to this photoelectron continuum state, or with 2 photons, those shown in green here, to the same final state. And we would expect that the relative phase between these two then should help us control. And note that the initial state and the final state have to be the same. So we expect interference in the case of the red and the green, but not with the blue. And we tried this idea, and we took a real molecule, and we took the inspiration from the experiment in Frankfurt. So this is a substituted methane. So where some of the hydrogen atoms have been substituted by halogens to make the whole methane structure chiral. And we look at the ionization of methane, chiral methane, using this parameterization of the electric field of the laser or Curie pulse that ionizes the molecule. And we started with a bichromatic gas, which means a gas where we have one frequency, and then, let's say, one frequency, the green one, and then double the same frequency. So the initial pulse contains the red and the green pulse. And we do get a signature of the chirality, this PECD, of about 4%. And we can check, do we have interference? And indeed, if we compare the contributions from the 1 photon and the 2 photon excitation, we see we have interference, but it's destructive, because the signs here are different. So then we use ideas from optimal control and change the parameters of this field and get an optimized bichromatic excitation, and you see that we can push the effect from 4% to about 20%. And if we check for the interference, that now we see indeed these contributions all line up. They all have the same sign. So we now turned the destructive interference into constructive one using the parameters of the external field. And then we told ourselves, well, nothing requires us to use these specific constraints on the frequency, these omega j's here. Let's just freely optimize. And then we obtained what you see now here on the right, and that is almost 70% of the effect. So we get a huge increase, and we interpret this as even more constructive interference. Now, let me show you that this interpretation is indeed correct. So here's the spectrum of the ionizing pulse after the optimization. And you see that we have two components, a low frequency part and a high frequency part. And the low frequency part, and in this case we were kind of lucky, is linearly chirped. So you see that you have here the spectral phase is just a linear function of the photon energy. And that's very nice because now we get for the yellow slope, we get this huge chiral signal, but we can of course shift this slope by hand and then check what happens and see that we reduce it to very small numbers like 6%. And changing the slope in the spectrum corresponds to changing the time delay between these two parts of the pulse, these two spectral components. And then we record oscillations of our chiral observable as a function of this time delay. And now how can we connect this to interference? Well, if you start with the low frequency part of the pulse, which is color coded in red here first, then you have only a single intermediate state that can be accessed by this photon, and you get interference between these three arrows here, which all end up at the same final state, at least within the bandwidth of our excitation pulse. But because you have the first step is the same for all three, there's no real effect of control here. If the high frequency component comes first, then you see that you can access all of those intermediate states and then ionize with the low frequency photon, ending up at the same final state. And now we can vary the phase between these three excitation pathways, and that gives rise to the oscillations here where you have destructive and constructive interference. And the biggest effect we get, what is shown here in yellow, if we combine all of those excitation pathways and adjust the phases and then get those 68 or so %. Okay, so when I showed these results to my experimental colleagues who know and are familiar with the ideas of coherent control, they said, well, this is really very nice, but look at these pulse shapes. This is nothing that we can easily do in the experiment, because the excitation is in the XUV and you can't shape pulses. So we sat back and said, well, what have we learned so far? We know that we need interference between different pathways, but we can generate these interferences and these pathways also differently and borrow from the field of attosecond physics a technique which is called rabbit. And never mind what the acronym is, I wrote it out here. The basic idea is that you're ionizing with a frequency comb, which has these purple lines here. And on top of this frequency comb of XUV frequencies, you add an infrared laser. These are these small red arrows. And then the total excitation is given by the sum or differences of those arrows. And you see now, for example, if you excite with this arrow and then add an infrared photon, you end up at the same state as starting with this arrow and subtracting or emitting an infrared photon. So at those sidebands, you do have the kind of interference that we were looking for. And if we do this now for chiral molecules, indeed, we get our PCD signature, and the strength, let's say here 12 and here 30, depends on how we choose the polarization directions of both the XUV and the infrared. And why is this more realistic for an experiment than what we showed before? Well,
you have 5 minutes.
Okay, this combination of fields is something that has already been done in the experiment, and the overall signature is very robust. And let me skip over the rest of what I wanted to show for this part, because I think it's still worth to go to the other half of my talk, even if quickly. So here I just want to highlight that this has been work of my former student Esteban Götz in a very nice collaboration with Lauren Greenman at Kansas State University. Because I wanted to make the point that this photoelectron circular dichroism, where you ionize chiral molecules, is closely related, surprisingly, to microwave three-wave mixing. And what they share is that in both cases, you have a vector observable that is expressed as a triple product. So what is this microwave three-wave mixing? Here's another chiral molecule, which has a permanent dipole moment, shown in gray here. And this permanent dipole moment has three non-vanishing projections on the Cartesian axis, shown here by the blue, red, and green. And if you excite with microwave radiation transitions involving two of those dipole moments, and then you collect fluorescence from the third direction, you see that if you do this for left-handed and right-handed molecules, the signals have a phase shift by 180 degrees or by pi. And this phase shift can be used for enantiomer selective excitation of the molecule. And that's really surprising. Why? Because left-handed and right-handed molecules have exactly identical spectra, except for something of the order 10 to the minus 12, which is due to parity violation. And yet what we want to do if we want to excite enantiomer selectively is we want to use the same set of electric fields and bring the right-handed molecules, for example, to this energy level and the left-handed one to that one. And that's possible if you use the same idea of pathway interference. Because in three-wave mixing, again, you have a two-photon pathway and the one-photon pathway, and it's the sign between those two pathways that makes the difference. And now the molecules, they have the same spectra, but the dipole moments, one component, let's say this one here, changes sign if you compare left-handed to right-handed molecules. And that you can use for this enantiomer selective excitation. And you can actually work out that the third order response that you need to describe this three-wave mixing process, again, is a triple product. So this is something which is really characteristic for chiral vector observables. And an experiment had been done already about 5 years ago, showing that the basic principle works. You can do this enantiomer selective excitation, but look at the efficiencies is very small, 10 to the minus 3. A little bit later, a second experiment was done at lower temperature, and now they're at a few percent, but still a small effect. So the whole effect is limited by temperature and by another fact that I come to in a minute. Let's first look at temperature. The problem is that even at temperatures as low as 1 Kelvin, this is the thermal population of all the rotational states that you're addressing in this microwave three-wave mixing. So the problem is that the levels which are excited in your microwave three-wave cycle are already thermally populated, and this thermal population cannot be used for coherent effects. So then we came up with one solution and say, well, just go to states which have no thermal population. For example, use rotational states which are vibrationally excited, and then the thermal population is 0 and you're done. Recently, an experiment has been done here in Berlin, just 500 meters down the road, where they used a different solution. Instead of going to levels which are not populated by themselves, they just blasted away any thermal population that was there by a laser prior to doing the microwave mixing. And see, they pushed up the efficiency to about 50%. But yet, if they continue to do what they do, they will never get to 100%. And the reason is that there's another problem, which is that of orientational degeneracy, because of the various orientations the molecule can have in space. You have to look at the orientational levels of the molecule. And they have different Rabi frequencies. Some transitions are forbidden. So for some of those M quantum numbers, you cannot close the cycle. And you're driving multiple transitions all at once. And now we asked ourselves, well, maybe we don't need just 3 electric fields to do this microwave 3-wave mixing. Maybe we need more. And can we find out how many fields we need to drive one enantiomer from any given initial state, let's say this one, to a final state that is different than for the other enantiomer. So they both start in this state, and then the red enantiomer ends up here, and the blue one ends up here, and they are driven by the same external fields. And we've teamed up with some colleagues in math to answer that question. And the answer is, if you just want to control this within a single enantiomer, go to any state, no matter which, you need not 3, but 4 combinations. And combinations means here polarization, direction, and frequency. And if you want to do this enantiomer selectively, then you need 5 different combinations. And then we can generalize the 3-wave mixing sequence they had before in the experiment. And I will skip over this now quickly. But these pulses do what we want to do. They bring one enantiomer to one final state and the other one to another final state. So we really separate. And now we can do this with 100%. And what we realized in this mathematical analysis is that you can achieve the same goal with an even simpler solution, not using so many pulses as shown on the previous slide. If you can use circular polarization, which should be okay with current microwave technology, and then the pulse sequences look like this, where you have to change the duration such that you synchronize the excitation. Okay, so this is work that was done in collaboration with Monica Schnell at DESY and Ugo Boscain and Sigalotti, Eugenio Pozzoli in Paris, the mathematicians, and by Monica Leibscher in my group. Now, what I want you to take from this talk is that what we've looked at so far are 2 very different experiments, one using microwave radiation, one using XUV, or at least UV excitation. But in both cases, it was these triple products of molecular vectors that were important. And this is a lesson that we have recently been able to exploit even further by answering the question, can we make a molecule chiral and probe its chirality? And to be more precise, we should ask, can we make molecules, plural, chiral and probe their chirality? Because in the end, in the experiment, there will always be more than one. And the answer is yes, with the vector observable, if you can find a triple product that doesn't vanish. So let me just move through this very, very quickly to give you an idea. We start from a planar molecule. So here, all the atoms making up the molecule are in the plane. And we can make this molecule chiral if we excite the central carbon atom in a vibration out of the plane. Then at some point, if it's up here, it's right-handed. And if it's below the plane, it's left-handed. And we can do this by creating vibrational superposition states. Now, if we had a single molecule, then an infrared excitation, for example, just from the ground state to the first excited state, creating a 50-50 superposition would be enough. But then if we average over many molecules, we would have as many left-handed as right-handed ones, and we would not get a net signal. So what we need to really see a signature, a chiral signature in an ensemble of molecules, is we have to look at the rotational average expectation value. And here it turns out that we need to make sure that we have such a triple product which doesn't vanish. And one way to realize it is to create the vibrational superposition, not with an infrared field, which is the more obvious choice, but with a Raman excitation in the presence of an electric field, because then we have 3 different field vectors that couple to this 3 different dipole moment vectors in our triple product. And here's a proposal for an experiment that we have just brought forward. So we create a vibrational superposition with a first pulse, a pump, and then we ionize the molecules just like in the first part of my talk. And we measure the photoelectron circular dichroism as a function of the delay between the pump and the probe. And indeed, we see here, despite orientational averaging, a chiral signature that reflects the time-dependent handedness of the molecules that we have created. Okay, now with this, I really jump to my final conclusions. So what chiral molecules can teach us about quantum control is that we can see effects of quantum pathway interference, even for randomly oriented chiral molecules in the gas phase, and just using the electric dipole approximation if we have the corresponding triple products. And I've discussed this for photoelectron circular dichroism and three-wave mixing. And now we can use those tools to actively control molecular chirality. And with this, I thank you for your attention.
So thank you very much for this interesting talk. I'm sure there are some questions from the audience soon. So far, I don't see any. So you can use the Q&A chat to put your questions there to the speaker. So if there are no questions, then maybe
I can ask a question, because
yeah, please.
And I like the talk very much, and I like the subject very much about chirality. So more or less, you could help also to do chiral synthesis by using your well-defined chiral light plus. So could you really, it looks like, no, you could make a
well, you could extend exactly. So the last part, which I presented, in a way, if you, let's say, now we just probe the chirality, but if you would then enantiomer selectively, as my molecule changes from left-handed to right-handed, blast it away when they are left-handed, then you would be left with the right-handed. Yeah.
So in principle, you could use this technique to do this light-induced. Very nice. Thank you.
Thank you.
So I have one question in the Q&A, which is quite technical. Which module software you used for your calculations, and do you think your results are very close to experimental results?
Okay, so let me start with the second question, because that's maybe more interesting for all of the audience. For the microwave three-wave mixing, we are very close to the experiment because we know the Hamiltonian extremely accurately. The molecular parameters that you need for microwave three-wave mixing spectroscopy are known. Okay, and this is the input of our calculations. So there, I'm just waiting for Melanie Schnell's group at Hamburg to do the experiment. And I'm confident she will. For the last part, making the molecule chiral, we had to calculate the electronically excited state. So there's some error bars, and then it's a little less obvious how to turn this to the experiment. And for the first part, the very first scheme on control is probably not going to work in the experiment as we predict, because our model for the molecular structure that we can come up with has such big error bars that the effect is there, but probably not at exactly the spectral components that we have in our calculations. And that was the whole reason why we went to this rapid scheme, where you combine the XUV with the infrared, and then you're more independent of the specifics of the molecular structure. So that second part, not only do we believe it works in experiment, but we've started to discuss with an experimental group in Zurich, and they seem to see the effect, but it's still work in progress, so I won't say more than that. The software that we use is home written, so it's our own packages.
Okay, so thank you very much. I don't see more questions. So if you have further questions to Professor Koch, you can still write in the Q&A and she will answer this afterwards. So we will have now a short break of about 9 minutes, and then we will continue with the sessions. So thank you, Professor Koch, for the interesting talk.